Salam and welcome everyone. So today we're going to be working on the question on the screen that says when 3.0 mole of O2 gas is heated at constant pressure of 3.25 atmosphere, its temperature increases from 260 kelvins to 285 kelvins. Given that the molar heat capacity of oxygen gas O2 at constant pressure is 29.4 joule per mole Kelvin, calculate the value for heat, the value for change in enthalpy, as well as the change in internal energy. So in this particular question, we're asked to basically calculate a whole bunch of stuff. So we're given information, basically numerical values, and that's what you're supposed to do anytime you have a science-based question. You're supposed to write all of the numerical values that you're given. So the number of moles is just 3.0 mole, okay? And then you have a constant pressure of 3.25 atmosphere, and then you have a temperature increase from 260 Kelvin, and then you have a final temperature of 285 Kelvin. Given that the molar heat capacity at constant pressure is just Cp comma m, because this is actually a molar value, so meaning molar heat capacity. So that's CPM. If it's just heat capacity, then it's just going to be CP. And hence the P here that you're seeing is just simply pressure. So if they ask you for the molar, if they tell you the molar heat capacity at constant volume, so what you end up with CVM. If they tell you the heat capacity at constant volume, then what you have is CV. So here we have Cp comma m. So molar heat capacity at constant pressure is going to equal 29.4 joule per mole Kelvin. So yeah, that is it. So we are asked to determine the value for heat, the value for enthalpy, as well as the value for internal energy. Well, I want you to guys to know something. First of all, if we can determine the value for heat as well as the value for enthalpy, then we know that we have the exact same answer. So if you determine the value for heat, right, because we're dealing with a constant pressure problem, note that the enthalpy is actually just heat at constant pressure. So basically, if we find heat or if we have enthalpy, we have actually automatically found the other. And then, of course, this does not apply to change in U. We still have to do more calculation to do that. So yeah, that's it. So to do this, we have to write the formula Q sub P. So the heat at constant pressure would just be the number of moles times the molar heat capacity at constant pressure times the change in temperature. So Q sub P is just N is just 3.0 mole. And then Cp comma M is just 29.4 joule per mole Kelvin times change in temperature, which is just 285 Kelvin minus 260 Kelvin. So yeah, that's basically it. So Q sub P is just 3.0 mole. Okay, I'm just gonna rewrite this times 29.4 joule per mole Kelvin times, okay, 285 minus 260 is just simply going to be 25 Kelvin. So of course you cancel out the Kelvins, cancel out the mole, and then Q sub P is just simply going to be 3.0 times 29.4 times 25 is just simply 2,205 joules. So that is basically the answer to this question. And of course, because we're dealing with a chemistry question, let's not forget that we're supposed to put in the lowest number of significant figures based on what we're asked. So if we go back to our question, we have 3.0 mole is in 3 sig figs. We have this in, sorry, 3.0 mole is in 2 sig figs, 3.25 is in 3 sig figs, and then 29.4 as well as 260, 285 is also in 3 sig figs. So we have to put our final answer in 2 sig figs. So Q sub P is just going to be 2.2 kilojoule. So that is basically the answer to this question, 2.2 kilojoule. So we've determined heat at constant pressure. Now we have to do change in enthalpy. So heat at constant pressure, which is also change in enthalpy, is just going to be 2.2 kilojoule. So that is basically the answer to this particular question. Now we have to go to our second information, which is to determine the change in U value. And to determine the change in U, we have to remember that change in U is the same thing as Q plus W, meaning Q sub P plus W, because of course this is a constant pressure problem. So we already have the value for Q sub P. We've calculated that. we don't have the value for work, so we're going to determine work. So we have to determine work, we have to remember that work done generally has negative P change in V as the formula. So yeah, as the formula. So we have to determine the pressure, or we have to substitute the pressure as well as the change in volume. Well, if we remember, we know pressure is just 3.25 atmosphere. So let's remember that pressure is just 3.25 atmosphere. But because we're dealing with a question where our final answer is meant to be in either joules or kilojoules, we cannot use the atmosphere, the volume of atmosphere for pressure. We have to change it to something that is going to make our units of work done to be joules. So here, if we put atmosphere, we're going to not, it's not going to be easy for us to determine what our final answer would be. So what I'm trying to say here basically is this: the best unit to put our pressure is going to be Newton per meter squared, or Pascal, right? Pascal or units per, sorry, or Newton per meter square. And then the best volume we can put, change in volume, is just going to be meter cube. So you cancel out meter squared and cancel out the cube here. So you end up with Newton meter, which is the same thing as joules. Newton meter is simply joules. Do you understand what I'm saying? So Newton meter is simply joules, and yeah, joules is Newton meter. That's basically yeah, that's basically everything. Newton meter is simply joules. So if that's the case, then we've gotten the proper units that we want. So we have to change pressure from atmosphere to Pascal, or to Newton per meter squared. So when we do that, then we have to also make sure we have our volume change in V in meter cube for us to be able to properly substitute. So we have pressure, again, is 3.2 atmosphere. We have to remember 3.25 atmosphere. We have to remember that 1 atmosphere, okay, if you remember your pressure units conversions, it's not going to be hard for you. 1 atmosphere is equivalent to 101,325, okay, Newton per meter squared. So that's basically it. So hence, this is just the standard information. Then 3.25 atmosphere is going to give you what? X. So let's simply cross multiply. We have X is equal to 101,325 Newton per meter squared times 3.25 atmospheres divided by 1 atmosphere. Divided by 1 atmosphere. So just cancel the atmosphere. So 101,325 would just be X is equal to what? So you have 329,305, sorry, 329,306, 0.25 Newton per meter squared. So this is the value for pressure that we're looking for. So this is the value for pressure that we're going to basically substitute this. Yeah, that's basically it. Yeah, that is the answer. So now we're going to deal with a change in volume. The change in volume is just simply going to be V final minus V initial. So when we go back to our question, you see that we're not given an initial volume as well as a final volume. So what this is telling you is that you're going to end up having to calculate it first before we can go further to substitute or do whatever we need to do. When we're calculating for V final is just basically NRT, or nRT final, divided by P. We know that the constant pressure exists. We know that the number of moles are R, and also T initial. We know the T initial to simply be 260 Kelvin, right? So number of moles is just 3.0 mole, okay, times 0.08206, okay, 0.08206. I'm gonna first of all do the V final in dm cube or in liters, and then I'm gonna convert from liters to meter cube, or dm cube to meter cube, because liters and dm cube are actually the same thing. So from dm cube to meter cube, but that's gonna be at the end. So just bear with me. So 0.08206 is same, is just the gas constant. So it has atmosphere dm cube per mole Kelvin times T final, which is just simply 285 Kelvin. So T initial is 260, T final is actually 285 Kelvin. There's a temperature increase divided by our beloved pressure, which is just simply 3.25 atmospheres. So cancel out the mole, atmosphere, Kelvin, Kelvin. So V final is just simply going to be 21.5881 dm cube. So that's basically the answer here. Now we have to determine V initial, but we have to remember that this is a constant pressure problem. And if you remember the combined gas law, we whenever we have a constant, we can just remove whatever that constant is and just write the equation independent of whatever is constant. So now we're going to use the combined gas law. We know what PV, okay, equals nRT, right? That's the gas constant, but we also know that Pi Vi is equals to over Ti, while Pf Vf over Tf. But we have our pressure to be constant, so we're going to remove pressure from this. So what we end up with is just going to simply be Vi over Ti is equals to Vf divided by Tf. So V initial divided by T initial is equal to V final divided by T final. So yeah, so the V initial is what this is what we're looking for. So I'm just gonna have V initial to be V final, okay, T initial divided by T final. So yeah, that's how you do it. So of course you substitute. So for V initial, you have V initial is just simply going to be V final, which is 21.5881 dm cube, 21.5881 dm cube times T initial, which is just simply 260 Kelvin divided by T final, which is just 285 Kelvin. So you cancel out the Kelvins, and yeah, you can determine V initial like this. V initial is equal to 21.5881 times 260 divided by 285. So you end up with 19.6944 dm cubed. So yeah, that is basically it. Now we have our V initial as well as our V final. So we know change in V, which is V final minus V initial, is just going to be um 21.5881. So 21.5881 dm cube minus 19.6944 dm cube. And when you do the calculation for that, you have the change in V to actually be 1.8937 dm cube. So yeah, that's basically it. That's basically what we're doing. Now you're going to be wondering, okay, yeah, we're basically almost done. We can just simply substitute work done is equal to negative P change in V. But then our work is not actually done because we remember how I explained to you that pressure has to be in what Newton per meter squared, right? Remember? And then volume has to be in meter cube. So we have to go from decimeter cube here. Okay, we have to go from decimeter cube here to meter cube. So we know now that 1 meter cube, okay, is this equivalent to 1000 decimeter cube. And the reason we know this is because 1 meter is equal to 10 decimeter. Hence, 1 meter cube, which is 1 times 1 times 1 is 1 meter times meter times meter is meter cube, is equivalent to 10 times 10 times 10. So 10 decimeter cube is 10 times 10 times 10. That's 1000. Decimeter times decimeter times decimeter is decimeter cube. So that is basically it. So 1 meter cube is equal to 1000 decimeter cube. So 1.8937 decimeter cube is equal to X. So you cross multiply and then you have X is equal to 1 meter cube times 1.8937 decimeter cube divided by 1000 decimeter cube. So you cancel out decimeter cube here, decimeter cube here. So X is equal to 1.8937 divided by 1000. 0.001837 meter cube. So yeah, so this basically the value for change in V in um in meter cube. So W is just simply going to be negative P change in V. So W is just simply So not 309, sorry, 329, comma. By the way, I have this in my personal notebook. That's how I know where it is. 25. And of course, the unit is Newton per meter squared, just like I taught you earlier. Times the change in V, which is just 0.001893 meter cube. So cancel out meter squared, remove the cube. So W is equal to negative 329,306.25 times 0.001893.7. So work done is just simply going to be negative 623.607 Newton meter, or simply this is basically joules. So also negative 623.6072 joules. So that is basically the work done. Now changing U is simply, so changing U is simply just work done plus Q sub P. So changing U is just negative 623.6072 joules plus 2,205 joules. So changing U is just going to be this here. Remember how we had the Q sub P that I solved from the beginning, 2,205. I have to use the raw value rather than 2.2 kilojoules, just because we're trying to get our answer in joules. 1, 2, we have to use more of the raw data whenever you're dealing with chemistry questions. So of course, what we end up with is just 1,581.393 joules. And yeah, that is it. And of course, we have to also put this in what? 2 sig figs. So that's going to be work done, changing internal energy. I apologize. It's just going to be 1.6 kilojoule, or 1,000 1.6 times 10 to the power of 3 joules, or just 1.6 kilojoules. And basically, this is the answer to this question. I know it was really long, but bear with me. This is basically how you do it. Like, there's no other way to do it except this. So, yeah, that's basically it. If you have any questions, please put in the comment section. If you have any suggestions or concerns, also put in the comment section. If you're a student who has been following my videos, just know that this is from the Physical Chemistry Atkins 11th edition textbook, and that's where I get all my physical chemistry textbook. You should click into the description box if you want to buy the book, or if you want to click and watch over 90 videos I have already made on my channel from the Atkins Physical Chemistry 11th edition textbook. I also wanted to mention that if you're a student who's struggling in any of your STEM related courses, whether you're in middle school, high school, or college, make sure you email me at shahabitutoring@gmail.com. I'm a tutor who helps students succeed in all their STEM related courses, as well as I mentor students as they navigate their academic life. So if you want to succeed and you want to be the best version of yourself in academia, do not forget to email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.